So what we were looking at last time we were looking at things was objects that rotate that translate, that don't rotate about themselves. They just move in a linear sort of fashion. So let's have a look here now at objects that rotate only about some point. So what I've got here are just a number of objects. You see the impeller in the pump there on the left. That would rotate about a shaft. The windmill blades would rotate, as would this oil derrick here. So those are all examples of things that would rotate there. So let's have a look here back on 670 at this. So what we're going to look at is something that rotates about a fixed axis. So we could have an object here that rotates, let's say about some point A, not the center of gravity, but some point set off from the center of gravity. Now, what we can do to analyze this is we can do a few different things. First thing, we can always use that equation there, some of mg is ig alpha. So what we would be doing, even though it's rotating about A, is taking moments about g. And you can always do that, and you can always apply that equation. Now, that would get a little tricky, though, because you would have the reactions at A, what we call dynamic reactions, that you'd have to analyze. Okay, so when you have fixed axis rotation, it's far more common to take the moments about the point you're rotating about. It just simplifies things a good bit. So if you do that there, you would just take moments about A. And for fixed axis rotation only, what you can equate that to is I sub A alpha. So that only works when you're using fixed axis rotation. So if you're rotating about point A there, as I have it called out, you could take the moments about A and set them equal to IA alpha. Okay. So that's a common thing to do. It's a nice little kind of short equation you can use when you're analyzing this fixed axis rotation. Now, the other thing you can do here is sum forces, not just in the x and y directions, but you could also sum them in the normal and tangential directions and solve for the normal and tangential reactions there. And those are called dynamic reactions now because you analyze the object as it rotates about A. So what you'd be doing there would be to track the center of gravity and look at its normal and tangential accelerations. And those would enter into finding those reactions because those accelerations would be the normal and tangential accelerations of the center of gravity there. Multiply that by the mass and you get the MA part of the equation. Okay. So this is kind of its own special analysis method here, as you're working with fixed axis rotation. You can look at the dynamic reactions using sum of forces in the normal and tangential directions. And you can also look at alpha by using the sum of MA as IA alpha equation. So why don't we look at a couple examples of this. So let's say we've got a motor there and we're going to apply a 40 Newton meter couple to a plate. Let's find the angular speed of the plate after 4 seconds time, and I think I'm on 720 is where I'm at. Okay. So we've got a shaft coming out of the motor, a drive shaft, and the motor is going to generate a moment of 40 Newton meters, sometimes called a torque. So this isn't a pump, obviously, but it's kind of like a pump. With a pump, you got a motor shaft coming out that drives what you call the impeller right there. Similar thing, except instead of an impeller, we just got a plate there. All right. So what we're going to do with this is we're going to sum moments. That's going to be the moment coming out of the shaft, the torque, or whatever you want to call it. And what that's going to equal is I alpha. So we'll apply this equation now, okay? That's how we're going to analyze this. So to do this, we got to find I, okay? So what we're after here, we've got a plate, and that's what we're going to rotate. That's what's going to have this angular acceleration. Alpha is the plate. So you want to find I for the plate. Okay. So we're going to find for a plate down here, this set of equations. So which one are we going to use? We're going to use IGX, IGY, or IGZ for that one. It's going to be Z, yeah, because what we're working with is the axis that's normal to the flat part of the plate. And we're going to work with the axis about which it spins, which is this axis. So we want to be using IGZ. And what that is then is 1/12 m, the mass, times a squared plus b squared. Okay. So you're given the mass, and you got the two plate dimensions. And there's no transfer axis theorem or anything like that required here because you're just spinning about the center of the plate. So it's just a matter of applying that equation and you'll get the moment of inertia, okay? So 1/12 times 235 times the sum of the two sides in meters, because I like to stay in standard units here. So I don't want centimeters or anything, I want meters. So it'd be 0.4 meters squared plus 0.9 meters squared. And run those numbers, you come up with 19 kilogram meters squared. So that's the moment of inertia. And that's a shape property that's kind of hard to really define exactly what it is. I think of that as being a resistance to angular acceleration. So the higher that number is, the harder it is to make something spin. Okay. In the linear world, it's kind of analogous to mass, is what it's analogous to. But when you start rotating things, you look at that mass, but also how the mass is configured with respect to the point you're going to rotate about. Okay. So once you've got I figured out, you just go sum of mg is Ig alpha, because that shaft goes through the center of gravity, so that's easy enough, okay? So sum of mg is Ig alpha, and just like I've mentioned before, I got the static stuff on the left, just moments, that's a couple coming out of the motor, and then I got the dynamic stuff on the right, Ig and alpha. Alpha is the unknown. Now, as long as you're in standard units, you don't need to be worrying about the conversions there, but really we're using the fact that a Newton is a kilogram meter per second squared, and that helps us get the units to work out right. But the thing is, if you're in standard units, these things will come out, these equations, so you don't need to really analyze the units each and every time. As long as you're staying in standards, they'll come out fine. So what's going on here is we got 40 Newton meters is 19 kilogram meter squared times the unknown alpha. So alpha is 2.11. As I show here, the units on that is Newton meter, kilogram meter squared. What a Newton is a kilogram meter per second squared. Okay, so that turns out to be a kilogram meter squared per second squared. So the kilogram meter squareds on either side cancel, and what you end up with then is 2.11 with a nothing on the top and second squared on the bottom. And what the nothing is a radian, because a radian is a ratio between a radius and a circumference. So it's a unitless quantity. So we can fill in that blank on the top with radians. So what we get there is alpha at 2.11 radians per second squared. Okay. Now from there, if you want to find the angular velocity, that would be easy enough to do. So what you do with that is just go to kinematics. It's, we've done things like this before with some of the stuff we did earlier. But what you would have there would be what, omega, and that will equal the initial angular speed. We'll call that omega 0 plus whatever alpha is times the time. I mean, that's basically it. And we don't have any initial angular speed, okay? So we're starting from rest. And so we got the 2.11 And that's just radians per second squared. And again, keep in mind that a radian really doesn't have units. It's just a unitless quantity. And then multiply that by the time, 4 seconds. So when you work through that, you'll get, what, 8.44? Yep. And one of the seconds there on the bottom will cancel. So you just get radians per second. So that would be the angular speed there after 4 seconds. So we all right with that? So that's kind of the basics of this, and that's very analogous to F equals ma. I mean, it's a very similar type problem we're working through, except it's a rotational problem. So it's m equals I alpha. Okay. All right. All right. Now let's look at some dynamic reactions there. So let's look at an object that kind of rotates about a pin. And what I've got there is just a photograph of a Sharpie impact tester, which is just a big hammer that'll swing on that central pivot there. And it's used to test the energy absorbed by materials. So that thing swings through and then basically will break a sample. All right, so online, I'll post this video, so, have a look. And what we're really interested in here is the reaction on the bearings there as this big hammer swings through. So let's see what we can do to analyze something like that. So let's have a look here at that beam on top of that oil rig there. And let's do the same sort of thing with this. So we've got a 1,200-pound beam, and we're going to apply these two forces. Notice we've got a pin joint here with some links there, and a big old cable over there on the left. And let's just kind of simplify this as a beam. And we're going to apply these forces to the beam, and it's got the angular velocity shown, 1.8 radians per second there. So let's find the angular acceleration of the beam and the x and y reactions at the pin. Okay. So we're out of balance here. We're going to have an alpha. And so that's going to be key to figuring this thing out, is to find what alpha is. All right, so the weight here, we're in the English system, 1,200 pounds, so we'll divide it by gravity. That'll get us a mass in slugs. And then we're off center here with our pins. See, we're going to take moments about A. And that being the case here, we want to find the moment of inertia about A. So that'll be IG, which for a slender rod is 1/12 ml squared. Then plus the mass times the offset distance squared. So I got 1/12, the mass times the length of the rod squared. That would get us the moment of inertia about G. But the thing isn't rotating about G, it's rotating about A, so I'm going to use IA. So I use the mass times the offset distance, the 2 feet squared. And I add those together and I get the moment of inertia of that thing about point A. So this is how hard it would be. It gets us an indication of how hard it is to make that thing spin about A, is the idea here. Okay. Now there's a bit of a process with this one that we're going to kind of want to work through. And it's going to bring out a couple of concepts that we want to be sure that we understand. One of them is you go through the center of gravity, okay? You put the weight of the object and the accelerations of the object at the center of gravity. That's how you approach a problem like this. All All right, so I put the entire weight at the center of gravity, the 1,200 pounds at G. I've seen people, when they first start learning about this stuff, they'll want to break it in half and put part of the weight over there and part of it over here, but that's completely unnecessary. You'll get the same results by putting the entire weight at G, okay? So just proceed that way when you're working through one of these. So that's 1,200 pounds. And see, what I want to do, my goal here is to find how the center of gravity accelerates. All right, so to get that, I want to find alpha. So I'm going to need to find alpha. So I'm going to use some of MA as IA alpha. And I decided there to use clockwise as positive. Okay. So I got MA as IA alpha. And I just go ahead and kind of collect the terms here and find the moments that they create. 500 pounds has a 7 and 2, makes a 9-foot offset. I'm calling clockwise positive, so that'll be negative. And then I've got 1,200 pounds times 2 feet, and that'll be negative as well. And then I've got this pull over here, the 1,400 pounds times a 5-foot offset, okay? That'll be positive. And that'll equal 758, which is the moment of inertia about A times whatever alpha is.
Units don't quite work out.
Units,
pound feet to pound feet squared per second.
I've got slug, yeah, and yeah. Okay, so yeah, we've got the units on the right get kind of complicated, but you have to go through, you got to get pounds into slug foot second squared. It'll all come out in the wash. As long as your standard units are good.
I forgot pound wasn't mass.
Yeah, right. Slugs. Okay. All right, so we just go ahead and work the, do the multiplications over here, set that equal to 758 alpha. So we got a small net moment actually is 758 alpha, so alpha is 0.132, and it is rotating clockwise, so that comes out to be a positive answer. So there's alpha. All right, so we've got alpha, and we've also got omega. Omega is 1.8, alpha is 0.132. So what you want to do now is find how the center of gravity is accelerating. Everything goes through the center of gravity on these kinds of problems. So that's how I would want to do this. So I want to find AG, acceleration of center of gravity, tangential and normal, okay? So the tangential is alpha r. Now what r is, of course, this thing doesn't have a radius, it's a rod, but what we got here is r is the distance from the point you're taking moments about, which is A, to the center of gravity. So that's what we call r. Because G is rotating about A, r is that rotational distance, 2 feet. And then AGN is omega squared, so 1.8 squared times 2 is 6.48. So we got a normal and a tangential acceleration there of the center of gravity. And that's the deal with this. Go through the center of gravity, okay? Now why don't you put those on the sketch? Get those going in their proper directions and put them on the sketch up there and see what you come up with there. And just get them pointing in their proper direction. Remember, they're originating at the center of gravity. That's how this works. We apply the forces of the entire object, we apply them to the center of gravity. That's how you approach this. So they're both going to be attached to G there. And just get them pointing in the proper direction. We've got the magnitudes now. But a good sketch on this stuff's important. Okay. All right, so let's see, let's start with the normal. Is that going to be vertical or horizontal, that one? Yeah, horizontal, and which way, right or left? Yeah, it's to the right, okay? So there's the normal. You okay with that? Because as G rotates about A, which is what it's doing here, it accelerates in towards A because it's rotating about A, okay? And how about the tangential? Is that vertical or horizontal? Yeah, vertical and up or down. Yeah, that's actually up, which might seem a little counterintuitive, but it is, because see, we found alpha is this way, right? So that whole object is rotating clockwise. So with respect to A there, which is the fixed point that everything's rotating about, G's going up, okay? So we want to be sure to get those things on a sketch and go in the right way, okay? So we got 0.264 feet per second squared up, and then 6.48 feet per second squared to the right. Okay. So if you're doing this kind of dynamic reaction problem here, what your first job here is to figure out what's the center of gravity doing? How is it accelerating? That's really what you want to accomplish first. All right. And then once you've got that, it's just F equals ma again, is all it is. So kind of compartmentalize it when you go through it. Find alpha, find how the center of gravity accelerates, because what it's doing, it's rotating about a given point. And then once you've got that, draw that up nice and clean, and then F equals ma after that, okay? So what we're going to do here is go fx, right, will be positive, is magx. Again, you go through the center of gravity is where you go through. All right, and then we've got, so the only x force we've got is the reaction at A, rax, and that'll be the mass times the x acceleration. So that's 37.3 slugs times 6.48 feet per second squared. And that's all to the right, see? So what's happening is this reaction is to the right. Now, I was just showing in class here, if I just held a book between my index finger and my thumb and dropped it and let it rotate, my hand feels like it's being pulled out towards the book. What that means is the book is feeling a force in the other direction, pulling it in. Okay, those are equal and opposite for that reaction there. So this X reaction would be to the right. Okay, what essentially that pin joint at A is doing is pulling the center of gravity to the right. That's what you're forcing it to do. All right. So we good with that? Got any questions on that bit? Okay. All right, now again, I'm keeping that rule, the static stuff on the left, dynamic stuff on the right. So when I go sum of Fy, I put all the forces and weights on the left. So the unknown reaction at A, and then the two forces, the 500 and the 1400, and then the weight, all three of those are down, so they all get negatives. So, if I were doing statics, I'd just set that equal to 0, but I'm not, of course, I'm doing dynamics, but that's the stuff that would happen with statics, okay, on the left. Now, on the right, what I put is the mass times the acceleration. Now it's accelerating up, we already figured that out, and that has to do with how it's rotating basically. Well, it had to do, I guess, no, actually it had to do with these weights and how they all kind of worked out and how far they were from point A. but the net moment is clockwise here. So that made G rotate up with respect to A. So that gets a positive sign over there on the right. It's the dynamic stuff. It's going up, so that's positive. Okay, so I got the mass and the acceleration. So what that does is add just a little bit to the A reaction, just 10 pounds basically. Okay. So the fact it's accelerating affects the reactions. Okay. So we okay with that? Okay, so we found the moment of inertia, not about G, but about A. Because I know if things going to rotate about A, I'm going to analyze it about A. Then I did a sum of moments equation equals I alpha. So I'm going MA equals IA alpha. Now I can only do that for fixed axis rotation. That's the only time that you can apply that particular equation. You can go MG as IG alpha anytime you want. But if you want to do a point other than G to take your moments about, if you're going to use that simple equation there, it has to be fixed axis rotation. That's the only time it works. Okay, so we do a sum of moments equation, we find alpha, we got omega, so now we can see the tangential and normal acceleration of the center of gravity as it rotates about A. That's what we're doing there. So we apply everything to the center of gravity. That's the approach. Okay. So we figure those out, we get them put on the diagram, go in the proper direction. And once you got that diagram, I don't care whether it's rotating or not anymore. It doesn't make, all I'm doing is analyzing the diagram. So can I compartmentalize everything? And I just do F equals MA, and I put the static stuff on the left, dynamic stuff on the right, and I get my proper signs on everything, and everything will come out. Okay. All right. So that's how I approach this one. Yeah, question?
Where's that 2.68 come from?
The 2.68, that's alpha. It looks like a typo. Is this supposed to be, what do I got there? Oh, that's alpha. Is that the right? And that's what that is. It's 0.132. So, yeah, it looks like I busted that somehow. That's just supposed to be alpha. I bet I had an old problem. I've changed this thing around a bit. So, yeah, I think that's just a typo. So, thanks. 0.132, I think is what that ought to be. Thanks. It's funny how that crept in there. I'm not quite sure. I bet that's a typo. Usually I got a bunch of these little boxes in here like this. I'm covering stuff up, so I think I changed something around. Okay. So we good with that? Okay. So that's a certain problem type, and you just want to get used to kind of working through that. Okay. All right, why don't we, this will take a little while to get through, so why don't we take a bit of a break here, then we'll do this other one too. These rotational ones get a little involved, so we'll take just a little bit of a break here. Okay. So we'll start up in 10 minutes.